Welcome to today's episode on the Catalysis Revolution. I'm Amara, and we're exploring how advances in catalysis are transforming chemical reactions and industrial processes. Joining me are May, a catalysis researcher, and Jamal, a chemical engineer. Thanks, Amara. Catalysis is truly undergoing a revolution. We're seeing unprecedented developments in single-atom catalysts, computational catalyst design, and sustainable catalytic processes that are reshaping how we think about chemical transformations. From an industrial perspective, these advances are game-changing. Catalysis is involved in about 85% of all chemical manufacturing processes, so improvements in catalyst efficiency and selectivity have enormous economic and environmental impacts. Let's start with single-atom catalysts. What makes them so special? Single-atom catalysts, or SACs, represent the ultimate in atom efficiency. Instead of using nanoparticles or bulk materials, we're using isolated single atoms as active sites. This maximizes the utilization of expensive metals like platinum or palladium and can provide unique catalytic properties. The precision is remarkable. With single-atom catalysts, we can control the catalytic environment at the atomic level. This leads to enhanced selectivity and activity, and often allows us to use much smaller amounts of precious metals. How are computational methods changing catalyst development? Computational catalysis has become incredibly sophisticated. We can now use density functional theory and machine learning to predict catalytic properties before synthesizing materials. This dramatically accelerates the discovery process. The integration of high-throughput experimentation with computational screening is creating a new paradigm. We can screen thousands of potential catalysts computationally, then synthesize and test only the most promising candidates. What role does biocatalysis play in this revolution? Biocatalysis is experiencing a renaissance. Enzymes offer exquisite selectivity and operate under mild conditions. We're now engineering enzymes for reactions they don't naturally catalyze and combining them with traditional catalysts in hybrid systems. The sustainability aspect is crucial. Biocatalysts are biodegradable, renewable, and often more environmentally friendly than traditional catalysts. They're particularly valuable for pharmaceutical manufacturing, where selectivity is paramount. How are these advances impacting sustainability? Catalysis is central to green chemistry. New catalysts are enabling more efficient processes with fewer byproducts, lower energy requirements, and the use of renewable feedstocks. We're seeing catalysts that can convert CO2 into useful chemicals, turning a waste product into a resource. The concept of atom economy is becoming increasingly important. Modern catalysts are designed to incorporate as many atoms as possible from the reactants into the desired products, minimizing waste. What are the biggest challenges in catalyst development? One major challenge is catalyst deactivation. Understanding and preventing the loss of catalytic activity over time is crucial for practical applications. We're developing more robust catalysts and better regeneration methods. Scale-up is another significant challenge. A catalyst that works beautifully in the lab may behave very differently in a large-scale reactor. We need to understand and control mass transfer, heat transfer, and reaction kinetics at industrial scales. What does the future hold for catalysis? I'm excited about the convergence of artificial intelligence, automated synthesis, and advanced characterization techniques. We're moving toward autonomous catalyst discovery systems that can design, synthesize, and test catalysts with minimal human intervention. The integration of renewable energy with catalytic processes is another frontier. We're developing electrocatalysts and photocatalysts that can harness renewable electricity or sunlight to drive chemical reactions. How will these advances impact everyday life? The impacts will be profound but often invisible. Better catalysts will lead to cleaner fuels, more efficient manufacturing processes, and new materials. They'll help us address climate change by enabling carbon capture and utilization technologies. From a consumer perspective, you'll see better products made more sustainably. Pharmaceuticals, plastics, and chemicals will be produced with less environmental impact and potentially at lower costs. Thank you both for this enlightening discussion. The catalysis revolution is transforming how we approach chemical transformations, making them more efficient, selective, and sustainable. It's an exciting time to be working in catalysis. The field is at the intersection of fundamental science and practical applications, with the potential to address some of humanity's greatest challenges. Absolutely. Catalysis is truly the key to a more sustainable chemical industry, and the advances we're seeing today will shape the industrial processes of tomorrow. That concludes our exploration of the Catalysis Revolution. Thank you for joining us in discovering how these molecular matchmakers are transforming our world.